So now what we'll do is we'll kind of review a few known supervised classification methods which do not really depend too much on optimization theory, because again, if we have to do optimization, then we would need more time. So we'll start with this classifier called LDA, or often called as linear discriminant analysis, and I kind of told you about Fisher's experiment with an iris data set. So this is one of the first ones that was done back in 1936 itself, and he had come up with this idea which is called as linear discriminant analysis. So the whole idea is like, let's say there are 3 data classes, and these data classes can be represented in some in some basis or some vector space. So that's why I was covering all that linear algebra. You want to think of data points as members of a vector space. So here what's happening is we have 3 different vector spaces. We have 3 different classes: blue, yellow, and green, just for the sake of illustration. And you can even call them as just 1, 2, 3 if you want to be simple enough. And what we wish to do is, so the way LDA works is as follows. So LDA assumes that all these clusters are having a common covariance, common Gaussian covariance, but all these classes have different means. Okay, so their average values are different. So the yellow class has a different average value, the blue class has a different average value, and the green class has a different average value, but they all have like some sort of common covariance that they have. Mathematically, the way we represent it as follows. So we say that the distributions for the 3 classes are modeled as Gaussian with mean vector m1 and covariance sigma, Gaussian with mean vector m2 and covariance sigma, and again Gaussian with mean vector m3 and covariance sigma. The sigma is common to all of them. So we are assuming that their variances look the same. So they all are. So this circle that you kind of see, that's capturing how the covariance or the variance looks like, and that we are assuming to be the same. So how will LDA kind of work? So once again, the key difference between classical statistics and machine learning is that you will not have the values of m1 and sigma given to you. So values of m1, m2, m3 and sigma are not given. That's the main difference. That's why it's data driven. The value of m1, m2, m3 and sigma are not given to you. So how do we kind of go around this? And that's where the training samples are useful. Okay. So the idea would be that there are labeled
covariance should be always equal. Common covariance is a necessary condition for LDA.
Yes. So it's necessary that the covariance sigma is common to all the 3 classes, only then it is LDA. If we assume different covariances, then that's called as a quadratic discriminant analysis, or QDA. So yes.
My question is concerned with I have a question. If the dimensionality is larger than the number of observation, if we have, can still PCA can be done with that eigen decomposition of covariance matrix?
No, so typically you would assume that, so your question is nice, so in the sense that what if I have less number of training samples than the dimensionality of the vectors itself, right? And this may often happen when you are looking at high dimensional data. There I think, yeah, the theory becomes much more complicated, and generally speaking, we want the number of training samples to be much larger than the underlying dimension of the data that we are looking at. But that is not always possible in some. I mean, so there are examples where the data is so high dimensional that you will not have enough data points.
Like I was having a particular real-time data set of brain connectivity issue, so I was analyzing the strokes, so there we were calculating the uniqueness components also. And
we
all
can
that.
probably chat about it after
Okay.
this one, but generally speaking, yes, if the data is if the data dimension is much higher than the the number of training samples that we have, then techniques like PCA would be very, very limited, because they assume that the entire data dimensionality has been explored. Other questions? Okay, good. So once again, in LDA, we assume that the covariances sigma are the same. But once again, because it's data driven, so the values of these vectors m1, m2, m3 and this covariance sigma, those are not given. So how do we get around that? Well, even if the values are not given, we do have training samples. So let us say we have x1, x2 to xn. So these are vector values. Generally speaking, this could be d-dimensional. So these training points are given, and possibly this could be, I mean, even though I'm showing them as two-dimensional, they could be, higher in dimension. They could even be scalar. Okay, so d could be 1 or d could be larger. So how do we compute? So, and all these points, these training points are labeled. So you know which point correspond to class 1, which points correspond to class 2, and so on. So how would you go about learning, let's say, the mean and the common covariance? So this is one way in which kind of Fisher proposed it, and that's why it's called as LDA. So you kind of approximate M1. So this is the approximation of M1 as the average of all the training points which are labeled as class 1. So you collect all the training points which are labeled as class 1, average them out. So N1 is the number of training points which are of class 1, so you average them out. That gives you M1 vector. So that's the first class conditional mean. Similarly, you can compute the second class conditional mean as all the points. This should be N2. This is a typo here. This should be N2, this part. So M2 hat is basically the average of all the points which are labeled as class 2, and so on. So you can compute these class conditional means. What about the covariance? Well, the covariance is common to all of them. So for class conditional means, we are using, we are kind of clustering all, we are using all the points which are labeled as class 1 only to get the class conditional mean. But for the covariance, we will kind of, use them all together. So for each point xi, what we do is we subtract its class conditional mean. So mi hat here is the class conditional mean that is corresponding to the particular training sample that we have, and then take its outer product again with itself, and then average it all out. So this part is the averaging. That gives you the common covariance. If this looks weird, then just remember that if you are given, so let's say if these vectors were one-dimensional, right? Then how do we find the variance? We just look at the data point, subtract the empirical mean, square it, and average it out. That's how we get an estimate for the variance, right? So we are doing the same thing, except we are learning the so-called covariance. As opposed to variance, we are learning the covariance of this data set. And this becomes a good estimate. All right, so this is how you kind of initialize or calculate the parameters of the in an LDA problem. Once again, there are so in the way it has been illustrated, there are 3 different data classes, and for 3 different data classes, we have 3 different means and 1 common covariance, and these are the formulas by which we learn the mean and the covariance. But then what do we do? How do I kind of build the classifier from there? So what we have so far is that how do I learn the parameters of the LDA model itself? So this is how you would come up with the classifier. So you will start looking at the log likelihood for a Gaussian vector. Remember, yeah, this may be, I'll write down the PDF of a Gaussian vector. So PDF of a Gaussian vector, x at some point, let's say v, is consists of the following terms. So you will have, so let us say x was of dimension d, which is what we are looking at. So there's one part that depends on, so this first part depends only on the, the covariance properties. It's basically it's a number. So you have determinant of the covariance of x, and that shows up as the constant, and then there is a second part where you have a functional dependence. So it looks like, I mean, a slightly daunting formula initially, but it's simple enough. So there are two parts here. There's a constant that depends on determinant of the covariance of x. And then there is a second part where you are looking at, so this is the PDF, or the probability density function of x vector, which is d-dimensional. So what you have to do is you have to compute the what is called as a quadratic form. So you take the vector v, look at how far away it is from the mean of the vector x. So that's what v vector minus m vector is. And then you compute this quadratic form. So you have v vector minus m vector transpose multiplied with the inverse of kx vector, which is the covariance of x. And then again it is multiplied by v vector minus m vector itself. So because v vector minus m vector kind of shows up on the left and right, that's why it's called as a quadratic form. And this quadratic form is with respect to this inverse of the covariance matrix of x. All right. Now for us, the covariance matrix has been written as sigma, right? So the way LDA classifier works is, so this would be this is basically how likely it is for v vector to get realized, right? And that's what a PDF anyway shows, right? How likely is it for a v vector to realize? So for example, if there is a v vector such that this number is very small, then you know that that vector is not going to be realized. On the other hand, if it is, so for example, if v vector was equal to m vector, then this whole exponent is equal to 0, and that tells me that this vector has some realizability. On the other hand, if v vector is really far out, much away from the from this mean vector m, then for a Gaussian we know that those vectors are less likely to realize, right? So this idea is captured formally in this item called likelihood, and because we are dealing with exponents, so what we do is we take the log of the likelihood, which is again canonically has been called as log likelihood. So what you want to do is you want to look at, given a new vector x, once you learn the parameter of LDA using training samples, once a new sample x vector arrives, so that could be a test sample, then what you want to do is you want to figure out the log likelihood, or roughly speaking the probability that x vector will belong in a given class I. So that's what you kind of begin calculating. So there are two parts here. The second part is, if you stare at this formula here, then the second part is basically just the exponent here. All right, so whatever is the exponent here, that's the second part here. And that's coming because we are taking log likelihood. So if I take log of the PDF, the exponent kind of goes away, and that's why I get this term, which is minus half times x vector minus the mean transpose, then you have the covariance inverse, then again x vector minus the mean. So you have a quadratic form corresponding to x vector, the mean, and the common covariance. What exactly is this log of pi I? So this, in the training sample, all the points may not be, all the classes may not be equally likely, and that's what this pi I is kind of capturing. So what it's saying is that how likely it is for a class I to get realized. So what you do is you collect the number of class 1 labels and divide it by the total number of labels, and then you say that, well, that's the probability that I will even see class 1 in the first place. That's pi 1. Similarly, pi 2 will be the number of class 2 labels that I have seen, and then I divide it by the total number of labels. So that's the probability that I will see a class 2 label, and you kind of multiply that onto the PDF. That's your usual Bayesian kind of formula. So what's the probability of seeing class I? Once I have seen class I, what's the probability that x vector will belong to class I? And that's the entire log likelihood that we have. The LDA rule is that you want to maximize this log likelihood. All right. So given any new vector x, what you want to do is you want to arg max. Arg means argument, max is maximum. So you first maximize the likelihood over I. Whichever I is giving you the largest likelihood, you take that as the argument, and that's your class predictor for x vector. Now it so happens that if I change I here, you would notice that there's a term x vector transpose times sigma inverse times x vectors. So that's the so-called quadratic term. that term does not matter in this rule because this term is the same for all the classes that we had, right? Because again, the covariance is common, and so therefore this quadratic term does not matter in this LDA rule. Once again, these log pi I and all, these are fixed numbers, they are not changing. So what changes with x vector, which is the x vector is the what you call the test sample, right? Once the test sample comes, you want to compute this and then maximize some sort of argument, right? So while doing that, you realize that x vector sigma inverse times x vector, that which is the quadratic term, that does not matter in this LDA rule, and that's why it's called as a linear discriminant analysis. If this term would have mattered, then it would not be linear anymore, right? And that's what actually leads us to the so-called quadratic discriminant analysis. All right. So in quadratic discriminant analysis, again, the picture is very similar. So you have three different classes as before. I mean, 3 is just for illustration. You can have as many classes as you want, but this is just for illustration. But now you are assuming that different classes can have different covariances, which is shown or illustrated using different shapes of the covariances that we have here. So in terms of notation, we are assuming that the first class has a covariance sigma 1, the second class has a covariance sigma 2, the third class has a covariance sigma 3, and they need not be the same anymore, right? They can be different. So what can we do in this kind of setup? So it's very similar. So the first part is you compute the parameters. Parameters are M1, M2, M3. Earlier there was only one covariance parameter. Now there would be 3 covariance parameters, sigma 1, sigma 2, sigma 3, and so on. So how do you go about it? So once again, the class conditional means remain the same. So for each class, you just collect all the training points which are given and average them out. All right, so that gives us the class conditional means. Again, this should be 1 by n2. That's a typo here. For m2 hat, you will have 1 by n2. So you collect the class conditional means, but for covariances, what you have to do is you cannot use you have to compute individual covariances now, right? So you'll have sigma hat k here, and that's going to be the average. So the way we calculate covariance or variances is the deviation of any given point from the average squared, right? So that's what we are doing here. So this is x vector. So we look at its deviation from its intended mean, and the notion of squaring for vectors is basically taking the outer product. That's how we compute covariance. All right. So for any given xi vector in class K, we are kind of looking at its difference with respect to its class conditional mean, taking its outer product and then averaging it all out. That gives us individual covariances for all the classes that we have. And then again, using this this likelihood or this probability density function and the class I priors, which is the probability that I'll see class I, and that also you obtain from the training data set, we can come up with this QDA rule, which says that look, maximize the likelihood. The likelihood function still looks the same as in the LDA case. The only difference here is instead of having a common sigma inverse, which was true before, we have a different sigma inverse for each class I. So each class I has a different sigma inverse here. The rule is still the same. So you just have to look at the argument of the index I, which maximizes this log likelihood. Now, when will I see error? So we'll see error whenever, so if the points, if the classes are kind of well separated from each other, then both in LDA and QDA you will not see errors. But there would be a lot of errors whenever the variance kind of begins to exceed the separation of the mean. So that's something that we see in practice. So you may say, when do I kind of use LDA, when do I use QDA? So QDA actually appears to be a generalization of LDA, right? And because of that, you would feel that maybe it's better to do QDA than LDA, right? That's the first instinct that comes to mind, because QDA is more general, so you'd expect it to be more accurate. And so therefore it would seem like that maybe I should use QDA all the time. But that's not true. The reason being that it's all because of this this whole idea that everything has to be done in data-driven manner. In other words, there are these training points that are given, right, x1 to xn. From that, we end up computing these class conditional means, class conditional covariances in the case of QDA, or generally a common covariance in the case of LDA. All that means is that I'm trying to learn a lot of parameters before I make the prediction. So my prediction or my classification would be only as good as I have learned the parameters, right? If I learn the parameters approximately, my prediction is also going to be approximate. So even though QDA appears to be more general, one may ask the question, why are we studying LDA separately? Why not just begin with QDA and finish it off, right? And the answer is you have to keep track of how many parameters are we kind of learning here. And that's where the, the core argument is. So the number of parameters that we have, so let's say if we had P classes. So in all the examples we saw, we had P equal to 3. We had 3 classes. So just assume there are P classes. And let's say we have D-dimensional data. So if I have each vector as not being 2-dimensional or 1-dimensional, but generally speaking D-dimensional, there are a number of parameters that I need to learn from the training samples x1 to xn. In the case of LDAs, P times D. So this is basically the number of each mean, class conditional mean has D elements, and there are P such class conditional mean, right? So that's what gives the first term, that is P times D. That's a complexity of learning the individual mean vectors. And then the common covariance matrix has D times D plus 1 by 2 elements. So why is it not D square? Generally speaking, you would expect this to be D square, but it happens to be a symmetric matrix. A covariance matrix happens to be a symmetric matrix, and that's why you only have D times D plus 1 by 2 number of elements here. Alright, so that's the parametric complexity of how many parameters do I need to learn in LDA from given set of training data. If I look at QDA, then each class has a different covariance, right? So the class conditional mean complexity remains the same. So whatever we had P of times D, we still have that same P times D here. But then the class conditional covariances boost this term from D times D plus 1 by 2 to P times D plus 1 by 2, right? So there's a P-fold increase in the number of covariance parameters that we need to learn. And even if D is moderately large, like let's say D was equal to 10, D times D plus 1 by 2 is approximately what, like 50, 55? And if I had 10 classes, then the number of parameters swells from 55 to 550. So the number of parameters swells very rapidly, even for small dimension, small enough number of classes P and small enough dimension D. So it's very common practice to kind of see 10 or 20 dimensional data and multiple classes, in which case QDA has way more complexity than LDA. What does that mean? That means that I need way more training samples to get the parameters of QDA correctly. And remember, prediction would be better only when the parameters are calculated correctly in the first place. Yes, you had a question.
So what do you mean by the data samples from LDA?
Data samples are?
From LDA.
No, data samples are.
Next paragraph. Next paragraph. If data samples are from LDA.
Yeah, I mean, so what we are saying is like we are saying, I'll get there. I mean, I haven't gotten there. Yeah. Let me explain it first, and then maybe if you have questions. Yes. So if data samples are less, then QDA will lead to random errors in parameter training itself. So if I believe in QDA model and if I have less number of samples, then the parameter training itself is erroneous. So if the parameters themselves are erroneous, I'll end up calculating incorrect or approximate likelihood as opposed to slightly exact one. And if my likelihood computation itself is inaccurate, then my prediction will be kind of further inaccurate, right? So all this is kind of said that, if we have too many, so if we have less data samples, then QDA will lead to lots of random errors in the parameter training itself, which is often, so if you read machine learning or statistical learning literature, that talk about this bias variance trade-off every now and then. Bias is kind of like a systematic error which is there because your parametric training was not good enough, or the parametric model itself was not good enough. That's what leads to bias. On the other hand, if your parametric model is very good, but if you don't have enough training samples, then you will not be able to get the parameters corresponding to your model correctly. Those random errors are contribute to what is called as the variance, or the variance like mean squared error. So it contributes to the variance error. So if you have less samples, then you have, larger variance in QDA. So you'll have less variance. But on the other hand, if you have lots of samples, then, and if I kind of insist on using LDA, then I'll have a bias kind of error, in the sense that I could have used QDA, which will have a lower bias, but then at the cost of having a higher variance, because I have way more number of parameters here. Now, the other thing that happens here is, let us say that, and this is, hopefully this will answer your question also. So let us say, the data was coming from 3 classes having the same covariance, okay? So here the model is that the ground truth, which is kind of giving me the data, is having, let's say, multiple classes, but all the classes have the same covariances. But I still go ahead and model it as QDA, because I have, I have lots of training samples, and I believe that QDA is more general than LDA, so I still kind of go ahead and model it as QDA. So what this will do is, it will create 3 different covariances for the 3 different classes, when there should have been 1. So what I'm doing is, I'm kind of fitting the ground truth by a larger description. So the ground truth had only single description, 1 covariance sigma, and I'm fitting the ground truth by having 3 different covariances, sigma 1, sigma 2, sigma 3. That's called as overfitting. So basically, I'm like kind of overdoing the amount of fitting on the ground truth, and that's because I don't know the ground truth. That's a very common problem in data-driven problems, because we don't know the ground truth, so we don't know what corresponds to overfitting. So we try to come up with a model and the best fit, but depending on the ground truth, we may end up with overfitting. So we may have our model which is exceeding data's inherent dimension. That may happen. That leads to overfitting. So for example, if you remember that function regression exercise, I may be interested in a function with, so the ground truth may be a cubic polynomial, as we saw in the function regression example, but I may end up fitting it with, let's say, a 5-degree polynomial. Then I'm overfitting it, because I'm introducing a 5-degree polynomial to explain a 3-degree polynomial. So that's an example of, again, overfitting. On the other hand, if data samples are from a QDA setup, meaning if data was actually coming from a QDA setup, and we end up modeling it as LDA, then what would happen is that I'll have a common covariance sigma for all the classes, while ideally it should have been sigma 1, sigma 2, and so on. So even if I had lots of training samples, it will still lead to this idea called underfitting, where my model is missing the data's inherent dimension. So the whole idea is that data has some inherent dimension. If I underfit it, I'll not have a good explanation of the underlying model. And if I overfit it, I will have like a more complicated explanation of what actually the description should have been. Both are undesirable. So underfitting is undesirable because you kind of miss the data's inherent complexity, and overfitting is bad because you are kind of introducing unnecessary variables which require both training and learning, and then whatever error you make in training and learning when you overfit, they kind of come back and start contributing to the performance or the error that we saw. So overfitting will typically lead to variance kind of errors. Underfitting will typically lead to bias kind of errors. Bias is something that is a deviation in your model away from the ground truth itself. That is underfitting, or that is bias. And overfitting is when you are like adding unnecessary parameters, and that leads to a lot of variance errors. So that's overfitting. Is that clear now? All right. So that's LD and QDA. These are the first classifiers that we kind of know. And of course, a lot of it is now formalized. I mean, things like Gaussian vectors and log likelihood and training sample, these are not that well understood earlier on. Now, you may also say that this looks quite simple. I mean, is this machine learning? It turns out that even despite its simplicity, I mean, if you see LD and QDA, they look to be quite simple. So it almost seems like maybe it is not used anywhere, but that's not true. There have been many benchmarks against which either LDA or QDA, I think approximately in some, so there have been like a suite of some 30 canonical machine learning program back in I think 2010 or so. So people tried LDA and QDA. So they were not the universal winners, of course, but I think there were some 9 or 10 examples where either LDA or QDA would kind of prominently show up as one of the best. So in spite of its simplicity, I think they do a good job, and maybe like the first point of exploration. All right. So let's get into support vector machines. So support vector machines, I think, were introduced sometimes around 1990s to 2000s, and this was the way it works is by constructing what are called as separating hyperplanes. So the way support vector machine works is it doesn't do a Gaussian fit and all, because even though we are not assuming that the parameters of the Gaussian distribution are known, we are still assuming that the data is Gaussian. So it's a kind of a semi-data-driven method in the sense that we are committing to Gaussian distribution even though we don't know its parameters, right? The way support vector machines and all work is they don't assume any underlying distribution on the on the class conditional distributions. So in the case of LD and QDA, the class conditional distributions were assumed to be Gaussian. In support vector machine, that assumption will not be made, and that is that's basically a move from, let's say, kind of semi-data driven method towards a data driven method here. So once again, we have 3 data classes, which we kind of simply call as 1, 2, 3, or blue, yellow, green in terms of this picture. And what we want to do is we want to draw these so-called hyperplanes. So what is shown in red here? So we want to draw these hyperplanes, which in some sense which separates the data maximally. All right. So there are 2 parts here. One we have to understand what exactly is a hyperplane, and then what exactly is this maximal separation. How is it done? Can it be done efficiently given a set of points and so on? The other thing that may kind of make you curious is why are we only drawing hyperplanes? Can I kind of draw some wiggly or doodly kind of curves? And I'll just give you a glimpse of that also. All right. So let's kind of see what exactly is a hyperplane. How do we kind of define it? So for a given vector A, which is, let's say, n-dimensional, a hyperplane is defined as, so what you do is you take A transpose times X vector, and you insist that this inner product between A vector and X vector is 0. So what we are doing is, given any vector, we are looking at its perpendicular direction. So that's what a hyperplane is. So given any vector A, you're looking at its perpendicular directions. What will be the dimension of, so given n-dimensional vector A, what will be the dimension of this hyperplane here? So it's going to be n minus 1 dimension, because 1 dimension is, so given any vector space, you can break it into 2 parts, right? A part and its orthogonal subspace. So if I look at a vector and its linear span as one direction, then n minus 1 dimensions are still left. So if I look at the the number of basis vectors or number of orthogonal vectors that I can have in this set, it will be n minus 1. All right. So so this hyperplane is n minus 1 dimensional, and because it passes through the origin, so therefore it happens to be a subspace. All right. So a vector once again is a constant here. It has same dimension as X vector, so that we can take the inner product. If their dimensions are not the same, you cannot take the inner product. And 0, of course, yeah, is the origin or the constant. So once again, the hyperplane is a subspace of Rn with dimension n minus 1. And you can also interpret this A transpose X as an inner product. So what we are saying is that A transpose X being equal to 0 is the same as inner product of A vector with X vector is 0, which basically means we are looking at all possible X vector perpendicular to A vector. So hyperplane is the subspace. So it's basically a subspace which is subspace of Rn, which is orthogonal to the vector A. All right. So let me give you an example. So let's say this is the vector space R3, 3 dimensions. So we can look at, let's say, the hyperplane corresponding to this vector, which is kind of projecting outwards. So the orthogonal, so the hyperplane corresponding to this vector would be this 2-dimensional plane that we have, because if I pick any vector in this shaded rectangle in blue, then that is going to be perpendicular to the vector which is kind of protruding out, right? In terms of the usual coordinate geometry, you would say that if this axis is, let's say, the z axis, then z axis is perpendicular to the entire xy plane. So the xy plane is a hyperplane for any vector which is aligned along the z vector, right, or z vector. So hyperplanes are actually used for understanding support vector machine, and so SVM or support vector machine is, I mean, one begins building it by looking at separating hyperplanes for linear classification. All right. So it's a classification, meaning you still want to do a machine learning application, but you want to think of it in terms of, you know, linear prediction. So you want to make you want to compute, or your computation is linear. Now, often an affine version of hyperplane is used. So what do I mean by that? So one may not insist that the hyperplane that I'm looking at crosses through origin, and that's because if you again go back to this motivation, you know, the point where all these hyperplanes are meeting, I mean, the data may not, you know, have or be kind of circled around origin. It may be far away from origin, in which case you want to not insist too much on origin being part of a hyperplane. So, in the context of SVM, people use separating hyperplanes, which are, you know, so what you, instead of insisting that, you know, the inner product between a vector and x vector is 0, you insist that the inner product between a vector and x vector is some fixed constant c. So you start with a non-zero constant c. Constant c may as well be 0 in some application, but that is not insisted. And what we are saying is that the inner product between a vector and x vector, that is equal to the constant c. Aligned. So let's look at it a bit more formally. So I'll be sharing the PDF slides, I think, and they will hopefully have better equations than these. Yeah, I wish my laptop connected properly, but yeah, I don't know. Anyhow, so back to this. So let us say we have two classes. I mean, just to kind of illustrate how people build these support vector machines using these so-called separating hyperplanes. Once again, you bring in that constant c because you may not insist, or you may not want to insist that the separating hyperplane is crossing through origin, because that's a limiting assumption. You want to kind of get away from it. Sometimes the data may be non-central, meaning, you know, it may be deviated away from 0. In that particular case, if you're insisting that my separating hyperplane crosses through 0, you'll get a suboptimal or a bad result. So to be able to tackle that, what you don't insist on the separating hyperplane to cross from 0. So the separating hyperplane is the inner product of a vector with x vector, and that you insist is a constant. And then what we say is that, you know, there is this notion of a margin, which is just the inverse of, you know, the norm of the vector a that you are looking at. So in other words, a vector which is very small in length, I mean, those may be not that well desirable. So the way to understand this is as follows. So what you want to do is, so just think of two classes as kind of shown here. So there's a blue class and there is a green class. But it so happened that, so when we plot these kind of scatter points, we are again assuming at the back of our mind that there is some vector space in which these blue points have been obtained. Similarly, there is another the same vector space in which these green points have been obtained, which again has its grounding in linear algebra, which is what we are covering at the beginning. Now, from the training data, we see that, you know, one blue point kind of appears here and one green point appears here. Now, if this blue point was not here and if this green point was not here, it's kind of very logical to think of that, you know, I can fit any line, you know, I can fit any line to separate these two classes. But all the problem is happening because one green point has kind of wandered onto that side. If I try to draw a line like this, then I'll violate a few green points here. And similarly, there's a blue point here. So if I try to draw a line like this, then it will violate the blue point here. So how do we kind of, or how did people kind of tackle this problem? So the idea is that you begin thinking of, so what you do is, given a point xi vector, which is basically one of the training points here. So x vectors are all these training points that we have. So the first thing that we do is we calculate the inner product of x vector along the direction of A vector. So that's the first part. All right. And then what we want to do is we want to find two things here. So the first item that we want to find is what should be the direction of the separating hyperplane. So that's A vector, and we also want to find this constant C, because I don't insist on the constant C being origin. So I also want to choose the constant C as a result of some optimization program. So what exactly is that optimization program? Let's kind of focus on that. So hopefully the choice is clear, right? So once again, the setup is that a few training points are given. What we want to do is we want to compute the separating hyperplane, that's A vector, and the constant C put together. So when we are talking about separating hyperplanes, we want to learn both A vector as well as the constant C, both are kind of put together. What is given to us is these points, x1 vector, x2 vector, and so on up till, let's say, xn vector. So some n number of training samples are given. So x1 to xn are given. Their class labels are also known. So the first thing that we then do is, for a given choice of A vector, right? Let us say I somehow made a guess that, look, A vector was, or the separating hyperplane was A vector. Then the first thing I can do is I can start computing, whether my separating hyperplane, how will it kind of classify. So that's what this is. So here we are calling, let's say, the blue class as 1, the green class as -1. And what we are saying is that, look, take x vector, compute its inner product with A vector, and add some constant C. So this is what I have learned the the predictor or the separating hyperplane to be. And then I look at the sign. So that gives me yi's. All right. So whatever is positive, I kind of label it as blue. Whatever is negative, I label it as green. And then what we insist is the following. So think of this epsilon1 as kind of, the margin, right? So whenever you make an error, you kind of have this kind of margin. So what we are saying is that if I look at the prediction that I have, all right, so this yi is the prediction that I have, and if I multiply it by, the raw number that we kind of obtained here. So if I look at the sign, the sign is going to be plus and -1, so it ignores the actual value that you had, right? This value could have been 0.01, this value could have been 100. Both of them will give you a yi of +1, right? So what you do is you kind of multiply it back, and then you insist that this condition is met. So if I look at yi times the separating hyperplane's value itself, then I insist that this is greater than 1 minus epsilon I. So that's one part. But what do I do? So this is the constraint that we are kind of working with. The next part that we kind of say is that I want the margin of the classifier, which I measure again according to two terms. One of them is just the length of A. I don't want the length of A to be very small. I want the length of A to be somewhat large, so that the margin is not too bad. And that effectively kind of captures, how much. So I can have, more than one possible fit here, right? So I could have fit A vector to be in this direction, but that has a smaller margin. I want A to be kind of central, and that's where this margin term kind of shows up. So I want to have a good margin, which means I want to minimize this norm. And then there is a second part, which is saying that I also want to, so whenever a point makes an error, it kind of brings in an epsilon1. So I don't want too many of these epsilon1s and epsilon2s, okay? So you add up all these epsilon1s and epsilon2, and then you look at the inverse of the margin square, and you want to minimize this. How do you minimize this? You minimize this by choosing A vector and the constant C both. So once again, it's a choice kind of problems. You want to choose C, you want to choose A vector, such that the margin is large, which basically means the norm of, or the length of A vector is small, and the number of points which kind of flipped around and went far away, the sum total of that should also be small. All right, so these are often called as positive slack variables. And then you obtain an optimal classifier by minimizing this, subject to your decisions agreeing with whatever the hyperplane values were, with this kind of error, 1 minus epsilon I. And this you want to insist for every sample point. All right. You may say like, what is this constant C here? So this constant C is often called as a hyperparameter that you get to choose. Do you weigh errors a lot, or do you kind of care about the margin more? So if you care about the margin more, then C will be small. If you care about the number of errors that are happening more, then your C will be larger. All right, and that's what would lead you to. So then the question may be like, is this solvable, right? This is an optimization program. Is this solvable? And what people showed was that this can be solved efficiently using convex programs and so on. Part of the reason is because you are dealing with separating hyperplanes here. All right. Now you may also say that what do I do with multiple classes, right? So if I had more than 2 classes, then what would I do? So the most common one is you just look at pairwise SVM, right? So here you had like 2 classes. You could do pairwise SVM if you have more than 2 classes, and just using that you can get it's an SVM or a support vector machine for K class classifier, which basically means you have to solve an optimization program like this for every pair of competing classes. Now, sometimes it may happen that the data is not linearly separable. So here you can kind of see like there's a very nice decision boundary that I can make, except for a few errors. But if I don't have that kind of setup, what if the data is kind of mixing somewhat non-linearly? So it seems like that, yeah, maybe instead of drawing a straight line, I think it's better to draw some sort of curve. And so therefore you may feel that maybe I should look into non-linear SVM. The answer is yes, people have looked at it systematically, and those are often called as kernel-based SVMs. Kernel because in the sense that you think of this as output of some sort of a linear combination of kernel functions. So once again, linear algebra in the form of linear combination and kernels from function theory kind of show up. And these kernels will typically approximate any any boundary up to sufficient accuracy. All right. So for example, kernels based on wavelets.
Would this be a combination of small linear?
No, this is so the way this is approached. It's not. If you're thinking piecewise linear, then no, that's not the approach here. So the approach is more based on. So for example, you would take a universal predictor like a radial basis function or a Gaussian radial basis function. So we know that sufficient scales and linear combinations of such basis functions will approximate any smooth boundary. And so therefore you train your SVM or the net or the program to obtain the nonlinear or the parameters of those corresponding to those radial basis functions. So yeah, so the intuition is not, I mean, it's a good intuition that you think of this as like a piecewise linear boundary, but while solving for it, we don't do piecewise linear boundary. We kind of think of this as a linear combination of a suitable kernel, such as the Gaussian radial basis function and so on. Okay. Other questions? All right, so let's get back to PCA again before we end today's session. So, all right, so how does PCA work? So remember that compression setup that I showed you earlier. So what PCA does is, so a lot of the time when we were doing these classification algorithm like LDA, QDA, and SVM, we are assuming that we somehow have points mapped into an appropriate vector space, right? But when we were dealing with those MNIST images, I had argued already that there's a vector, so you can obtain an orthonormal vector or basis vector such that the coordinates decay down rapidly, which means you can obtain better compression of the images, right? So two questions kind of show up, like how do I obtain those Q vector? Then the other thing is, once I obtain those Q vector, which is the appropriate orthonormal vector set, which allows me to represent any image compactly or by image compression. Then the other part is, can I think of images lying in that particular vector space? Because if I can think of images lying in that vector space, then for example, for MNIST classification, after doing PCA, I can apply, let's say, SVM on top of it and that will give me a good predictor. So the answer is yes. So let's look at how PCA is done. So the motivation is as follows, and here again I will be using that spectral decomposition that we talked about. All right. So think of x1 to xn as the training samples, and there is some data dimension m that is present, right? So m is, and think of m as somewhat large. Like for example, for the MNIST case, m was 784, n was 60,000, right? That was the number of training samples we had, and goes back to the question that we had earlier also. So you still want to think n to be larger than m, so that you have, let's say, one representative point along each dimension at least. If you violate that assumption that n is, let's say, much smaller than m, then it's a separate and a more challenging problem, often dubbed as high-dimensional statistics. So, and what we want to do is we want to create lower dimension projections, or you can even say lower dimension mapping if you don't want to use the term projection. So the whole idea is like I want to come up with a map capital P. That's basically just a matrix which I want to multiply on this high dimensional data. So I'll end up obtaining P of x1, P of x2, and so on up to P of xn. And I want to do this while like kind of retaining the essence of the data. All right. So I want to still retain some essential features or essential version of x1 to xn here. All right. So the key questions that arise are like, how do I choose P? That's one. How do I choose the dimension that I'm going to have here, small p? And then if I do have a way to choose this both capital P and its dimension, then can I measure the fidelity of this kind of projection or principal components? All right. And once again, this is data driven. So think of those images 0, 1, 2, and so on, all those digits again. You don't want to assume some sort of model here. You don't want to assume that data is Gaussian and so on. I mean, many times PCA is actually developed by assuming that the data is Gaussian. That's fine. But in a general setup, that may not be the case, right? You may just be presented with training data, which is x1 to xn. In the case of MNIST, it's those handwritten digits. And then you just somehow want to kind of come up with this projection somehow. All right. So how do we do this? So the first step is you compute the average of all these points. That's what this xn average here means. All right. And so given training points, you can always compute the average. So this is not a big deal. So I can just compute the average and then look at the difference between each point with respect to that average and take its outer product, average it all out, right? So this will give you the covariance or the empirical covariance as we call it. So this Kn here is the empirical covariance of all these points xi. If you assume, for example, that the data set was, let's say, 0 mean, then the second term here would be 0, and then it's much more instructive. It's just xi times xi transpose, right? So this Kn is going to be of the size. So each vector x is of size m by 1. So what we are doing is we are multiplying m by 1 vector with its transpose, which is 1 by n. So this average will be an m by m matrix, which corresponds to the covariance or the common covariance of all these x vectors. All right. So, and this Kn happens to be symmetric, right? Because if I take Kn transpose, then I have this outer product, right? A vector times its transpose. If I look at a vector times its transpose and I transpose it, I kind of get the same thing back, right? So if I look at x vector times x vector transpose and transpose of this, then that's same as x vector times x vector transpose. And this you can verify using the transpose formula, as well as, I mean, A times B transpose is B transpose A transpose, and then further x transpose transpose will be same as x. All right, so if you put this down, then you would figure out that Kn is symmetric. And so therefore, from the spectral decomposition spectral decomposition meaning corresponding to eigenvalues and eigenvectors, whatever we had learned, we know that I can write down Kn as Q times lambda times Q transpose, where Q transpose is identity. So what is Q? So Kn has the set of eigenvectors u1 to um. M is the dimension now. All right, and so Q will be u1 augmented with u2 all the way up to um. So those are the augmented eigenvectors, and then I can represent this Kn as Q times lambda times Q transpose. Q transpose is identity, which means the columns of Q are orthonormal, which also means rows of Q are orthonormal, and so on. All right. So how do we choose? So given Kn, what I think they should have actually read P instead of Q. How do I choose P? So once again, remember what we want to do in PCA is that given x1 to xn, I want to map it down or compress it down to P of x1 to P of xn. And this map P is going to be P times m dimensional, right? Because if I take a P times m dimensional map on top of m dimensional vector, I'll get a P dimensional vector. So you want to think of P as something which is not tall, so it's short and fat. All right. So P is much smaller than m. So for example, m could be, let's say, 784. P could be 100. In which case, this matrix P is 100 by 784 in dimensions. You want to imagine like a short and a wide matrix. So from the previous part, we know that we can compute an empirical covariance, which can be further written down in this spectral form. And so the first thing that should be done is, rearrange this lambda matrix. Rearrange this lambda matrix, which is the it's a diagonal matrix, if you remember. So rearrange it so that the eigenvalues get sorted. Now, if you're looking at covariance matrices are symmetric, but they are also known to be positive semi-definite. If they are positive semi-definite, then we know that their eigenvalues are strictly non-negative. So we know that each of the lambda i's will always be greater than or equal to 0. So that's something again that we know about positive semi-definite covariance matrices. All right. So you rearrange lambdas such that they kind of get sorted. What would that mean in this representation Q lambda Q transpose? So each time you kind of swap two values of lambdas, you also swap the corresponding column vectors. All right. So in this representation, we are kind of assuming that lambda 1 is the largest. So you pick the largest eigenvalue. Corresponding to the largest eigenvalue, you have its corresponding orthonormal eigenvector. Then you select the second largest eigenvalue, and then you have the corresponding eigenvector, which is corresponding to the second largest eigenvalue. So you kind of assume that this is already done. And what that does is like it forces the last few eigenvalues to be really small and the first few eigenvalues to be really large. And that's where actually this name principal components kind of shows up, right? Principal in the sense that the first eigenvalues or the first few eigenvalues are the principal ones, they are the important ones. The later ones are going to add details, but if you are willing to compress at the cost of details, you can do that. So what you want, what the PC algorithm then is that you choose you choose P as the vertical concatenation, meaning basically this is the same augmentation. So you start with Q1, Q2, all the way up to QP, or U1, U2, UP in this notation on the board here. So you collect the first P eigenvectors. That's what Q1 to QP here kind of means. So you select P as this matrix here. So that's going to be no, I think that oh no, yeah. So it's a vertical concatenation, yeah. So you think of, so vertical means that you take Q1 vector transpose, Q2 vector transpose, and QP vector transpose, yeah. So that's how you get a P by M matrix. So that's what the vertical concatenation means here. So this, declare this to be your matrix P, and that will give you the principal component projection that you are looking at. So principal components can also be understood as the best in energy approximation, and that's as follows. So Kn is the covariance that you want to kind of capture. You want to capture it by some other covariance matrix X. So what you do is you start looking at the mean squared error. between k and nx. That's called as the Frobenius norm. That's what this F is for. So you're choosing X, a symmetric matrix X, which captures Kn best in the Frobenius norm sense, but you have a kind of a rank constraint on X. So you don't want the rank of X to exceed P, which is corresponding to the dimension that you have selected. So this is also often called as a low rank matrix approximation. So a lot of PCA literature or low rank matrix approximation literature starts with PCA and kind of goes in that direction. What we saw, PCA was for compression of vectors, but it can also be used for understanding, let's say, low rank approximation of positive, definite or symmetric matrices themselves. Any questions on that? So if you're wondering how did we obtain those, you remember when we did MNIST example, I had shown you that, there would be a canonical basis Q1 vector, Q2 vector, all the way up to Q784 vector, such that, the coefficients or the coordinates of the zero image that we saw, that will begin to decrease. And the reason it was decreasing is because we obtained, the principal components by sorting the eigenvalues. And that's why it was decreasing rapidly. And that's why we were able to achieve compression as well. So this was the method by which we had obtained that. So any questions on this, or otherwise I'll move to the last part, time permitting, I think. So let's look at, I don't know, I'll just go very briefly over it. So this goes back to the function regression that we had talked about. So there's this notion of a rank of a matrix. So rank of any matrix T is basically either the dimension of the row span of, this should be row span of T, and which is basically the same as dimension of the column span of T. What is column span? So you take all the column vectors, look at their linear span, look at its dimension, then that will be the column span. Similarly, you can compute the row span. So if a matrix is square, which basically means M is equal to N, where M and N are the dimension, then the rank of, and if the rank of matrix is N, then it has an inverse. So a lot of function regression is kind of concerned with whether I can observe the data and invert it to find a function, and that's why this notion of inverse is useful. So let's say if you are trying to solve y vector equal to a times x vector. This shows up a lot in engineering, and this is just the motivation for why we need something that is called as a pseudo inverse, which eventually leads you to linear regression. So if the matrix A is not square, then we cannot apply an inverse directly. So if, for example, A was square and I knew it is invertible, then I can just compute x vector as A inverse of y, but that may not always be possible. So these equations often show up in linear regression. It's a part of both machine learning or statistical learning, as well as it kind of shows up everywhere in engineering. Now, if M is larger than N, which basically means I have more equations than the number of unknowns. So x vector is the number containing the number of unknowns, that's equal to N. If I have more equations, if M is greater than N, then we need something which is called as a pseudo inverse. On the other hand, if M is less than N, if I have less equations than the number of unknowns, then the system is often called as underdetermined and cannot be solved unless you make more assumptions such as sparsity and so on. All right. So we have an overdetermined system of equations, and that's why we need a pseudo inverse. Now you may say, like, why not just throw away some of the equations from this overdetermined system so that I have a square matrix A. That can be done if the measurements were perfect. But generally speaking, again, you don't get to see perfect measurements. You would have noisy measurements, and that's where the pseudo inverse concept is again useful. So how do we solve for pseudo inverse? So if we have to solve for y, which is, let's say, a linear combination of x vectors, so y is given as a times x vector, then this is how we kind of solve it. So the first thing is you pre-multiply both sides by A transpose. So if A was M by N, then A transpose will be N by M. So you end up with A transpose Y, which is A transpose times A times X vector. And then we know that A transpose A is square matrix, right? That's going to be N by N. So overdetermined means M was larger than N. And so there would be a good chance that, this N by N matrix is invertible. So if we can invert it, then we will get X vector as A transpose A inverse times A transpose Y. And so therefore you would just end up declaring X vector to be A transpose A inverse times A transpose A times X vector. So it looks like a complicated enough formula, because this is almost saying that, look, X vector is equal to X vector. So the reason it is useful again is because, so if you see this formula, this looks dumb, right? Like it's saying that X vector is equal to X vector because I know that A transpose A inverse times A transpose A is going to be identity. So it looks pretty dumb. It's not dumb in the sense that if Y vector was not pristine, if it was affected by measurement noise, which often happens in a lot of engineering experiments. So you'll have Y vector as, A times X vector plus some extra noise W, often called as, let's say, a measurement noise. So if this is the setup, then this pseudo inverse is more useful. In which case, instead of the measurement as A X vector, so this is, by the way, the measurement part, right? Y vector is the measurement part. So instead of Y vector, which is A times X vector, I'm going to have Y vector, which is A times X vector plus W. All right. So now what happens is there's this first term which corresponds to X vector itself, and then there's some noise shaping that is going on. All right. So you want to understand this in two parts. There is a first term which is just X vector itself, and then there is a noise shaping that is going on. All right. So what can we kind of interpret this somehow? And the answer is yes. So the first thing that we are doing is we know that my measurement Y should be, so one way to understand Y vector is that Y vector is in the row span or the range space of A transpose. That's because Y is obtained after a linear transformation of X vector, which means so you can interpret this as follows, right? So we have x1. So if I think of X vector as x1, then x1 is multiplying onto the entire row vector of A, the first row vector of A. Similarly, x2, which is multiplying with entire second row vector of A, and so on. So that's what it means by saying this. So we map the observation along the range space of A transpose. So what is range space? So look at A transpose. So that's going to give you column vectors. And the linear combination of the column vectors is what you are going to observe, that we know. That's because of this equation. So I know that Y vector is always going to lie in the range space of range space of A transpose. Now we know that the ideal or the noise-free Y vector lies in this range space of A. So what this does is, when I multiply noise by A transpose, we are kind of saying that, look, so initially the noise is high dimensional. It's like measurement noise pointing in all directions. But by multiplying it with A transpose times W, we are restricting it to the range space of A, because that's where I know Y kind of lies. So this step will filter out the part of noise which is outside the range space of A. So that's what this A transpose times W is doing. The other thing is the component of noise in the range space of A, that cannot be filtered out. That's the second part that you should kind of keep in mind. And so unless more information is given, so beyond this filtering, which is A transpose times W vector, one cannot reduce the noise which is within the range space of A. So this is how, for example, you would do function regression. So initially when we saw those training examples, then we had seen function regression, and this is how you would kind of end up doing function regression kind of model. So in conclusion, what we did was we looked at some machine learning problems at a glance, and then we motivated, let's say, classification, clustering, and regression problems. We also went slightly over handwritten digit recognition problems. And then we reviewed the LDA, QDA, support vector machine, and principal component analysis method. And then we looked at pseudo inverse. If you look at starting textbooks, there are quite a few. So I would recommend that if you like the fundamentals part more, then you should look at this third book, which is Linear Algebra and Its Applications. That's by Gilbert Stein. So that will give you the necessary mathematical tool to begin understanding machine learning. And then the second book by Bishop, that does a very good job of explaining the underlying mathematical details. On the other hand, if you want more of a review or a summary of which books to look at, then which algorithms kind of do what, then you can look at the elements of statistical learning by Tipshirani, Hesti, and Friedman. And then if you're the upcoming area, and I mean in the past decade we had a lot of discussion around what is called as deep learning. And to understand that, then there is a very good textbook by Goodfellow, Bengio, and Coolville. One thing that I have not listed here is if you are interested in optimization theory itself, then there is a nice book by Stephen Boyd and Vandenberg. So you may want to check that out as well. All right, so that's it, I think. And I believe I'm nearly on time, so it should be okay. If you have any questions, feel free to ask right now. I'll also be right outside this room for some time if you have any questions, if you want to take offline. And if you have any further questions in the, while you are here or after you leave the campus, feel free to email it to me, okay? All right, thank you.